All right, so the work that I'm going to present today is called Model Distillation for Faithful Explanations of Medical Code Predictions. This is work that I presented at BioNLP this year, and I did it with Zach Wood-Dowdy and Mark Dudzi. All right, so this is the tasks that we're concerned with. So there is a bunch of codes called the ICD-9 codes, and it stands for the International Classification of Diseases. And it is almost 9,000 codes that are used for medical conditions and treatments. So whenever you go to the doctor associates certain codes with your visit, and that is used for insurance billing, health management, statistics collection, etc. And this is a multi-label classification task, so you can have multiple codes associated with each visit. So this is obviously like a really important task. There's pretty important implications for getting these codes right, but at the same time, there are nearly 9,000 codes, so this is also really tedious for people to do. So it'd be really nice if we could automate this. So the data set that we're going to be using is called MIMIC3. It is an anonymized data set of discharge summaries with ICD codes. And so we're going to use this data sets to do this prediction.
Quick question.
Yes.
I've heard ICD-10 being mentioned. Is that just a new iteration of this, or is that a different?
Yes. So ICD-10 is the most recent generation of ICD codes, and they introduced a lot more codes. So I don't remember the exact number, but they made it quite a bit bigger.
I encourage everyone later to Google funny ICD-10.
Yeah.
There are a lot, and
there's some really
like
specific ones.
To jet engine subsequent encounter. So you get sucked into a jet engine from the hospital.
I think that there's one for like attacked by pigeon or something. Like they get really specific.
Bitten by pig. Initial encounter. Struck by duck. Anyway.
All right. So the motivation for what we're going to do is say you have your discharge summary, you feed it into a model, and then the model tells you that this is the ICD code that we're going to associate with this visit. Because these codes do have important implications for how they're used, the doctor might look at that and go, why did the model make this prediction? It's pretty important that we understand that we get this right and that we understand why the model is making these predictions if we're going to actually be using it in a clinical setting. So the question is, can we make high-performing models more interpretable? I think that we've all seen this trade-off between interpretable models and higher performance. So we want to be able to take the highest performing models that we have on this test, but make them a little bit more interpretable. All right, so in order to do this, we're going to use knowledge distillation. So knowledge distillation is typically unrelated to interpretability. And the idea is that it allows for a big or expensive model to be distilled into a simpler model. So we're going to use knowledge distillation for the purposes of interpretability, but it's also been used for things like efficiency or such. Okay, so this is our model distillation method. So the typical setup for training a model is you have your input, you feed it into the model makes its predictions, and then the objective function for the model takes that and the labels into account. So what we're going to do is we're going to have our teacher model take in the discharge notes, and the student model loss, rather than taking into account the true labels, we're going to train it on the teacher model. So the important thing to note here is that the student model never actually sees the true ICD labels. All right, so then that leads to a natural question. What do we use for this? Yes. The idea here is that it's being trained to mimic the higher performing model. The original paper?
So we actually don't want the student model want it to match the teacher. So the teacher is really like making certain type of error. That's the first, as opposed to like a way of making patience.
One more thing, the way it's drawn, it looks like everything happens at once. I'm assuming that what happens, the blue stuff happens first, and after that it's frozen.
Yes.
And then the orange stuff happens with the left half of the blue stuff.
Yes,
If you put three those together, I don't know what that-
we could. That would be interesting to look at. Okay, so from the setup of our training, the natural question is, what do we use for the student model? And so we decided that we're going to use linear regression. The reason why we chose linear regression is because it's interpretable, it has known theoretical properties, it has minimal compute needs, so we can do this really quickly. We can represent the input as a bag of words, which later down the line we'll see allows us to extract explanations for the predictions. Yeah. All right, so now shifting a little bit to interpretability and how this relates to that. So interpretable machine learning has been widely studied, and there are two main and sometimes competing goals that we have. The first is faithfulness. So this is asking, does an explanation match the internal decision-making of the model that we're trying to explain? And the second is plausibility. So can a domain expert understand the explanation? So whenever we're looking at interpretable methods, these are the two goals that we're primarily concerned with. So as a baseline to our student model, we're going to train a logistic regression model that's trained on the true ICD codes. The reason why we think this is a reasonable baseline, it's because it's the exact same complexity as our student model, but it just sees the true codes as opposed to the teacher's predictions. So this seems like something reasonable to compare to. And for our teacher models, we're going to look at three different models. The first is Dr. Camel, which is a attentional CNN-based model. The second is Hans, which is a bi-GRU-based model. And then the last is Trans-ICD, which is a transformer-based method. And so the reason why we chose these three models is because they're all low interpretability, high-performing models, and they have different architectures. So we want to be able to see if our method works across different architecturals. All right, so in order to evaluate our student model, we want to look at a few things. So the main thing we want to ask is our student model a good student for the original teacher model that we're comparing to? So in order to answer this, we're looking at a few specific things. So first is, do the student model's real valued probability predictions correlate with the teacher model's predictions? How often does the student model make the same predictions as the teacher model? And how does the student model perform in comparison to the true ICD labels? Okay. So first, this is answering the question, do the student model's real valued probability predictions correlate with the original model's predictions? So this is the student model and the baseline model. And we can see like the student model significantly correlates higher with the teacher models than the baseline does. This isn't particularly surprising because it was optimized to do this, but this is maybe a good gut check that this is true. And then the second question is, how often does the student model make the same binary label predictions as the teacher model? So again, we have the students on the right and the baseline on the left, and we can see for two of the three models that we tested, it agreed more often with the teacher model. All right, and then the last thing we want to look at is how does the student model perform in comparison to true ICD codes. So we have our student in comparison to its original teacher. So not surprisingly, the student generally performs worse than the teacher because it is a simpler model. But what's interesting is that the student does outperform the baseline in 2 of the 3 models that we tested. So in a deployment setting, a clinician might actually choose to deploy our student model over the teacher model, even though it has worse performance because it's more interpretable. And it's still outperforming the baseline model of the same complexity. Yes. So I think that the intuition for why this is because since the teacher is higher performing, it's sort of like learning a little bit more like how to calibrate like those probabilities. That's my intuitive answer, but I haven't looked too much at like the theory for like if anyone's proven why that might be true. Okay. So for time, I'm just gonna go through this really quickly. Since we represented everything as a bag of words, we can extract explanations by just going through the input document with a sliding window and taking the argmax of the feature importances. And we see that the student gets really similar explanations to the original model. And we're also able to provide explanations for models that weren't originally designed to be able to do so. And I'm going to skip through all of that.